Okay, welcome to IA 201 Motors and Controls. Today we are diving into chapter 12 in the book Contactors and Magnetic Motor Starters. In this book, we talk about what a contactor is and also a magnetic motor starter. We are going to tear apart a combination contactor magnetic motor starter tomorrow. We're going to look at the insides on the cam. We're going to talk about how they work when that happens, but the book provides you a lot of important theoretical knowledge and also wiring diagram information and a lot of really good data. So this is starting on chapter 12, page 237. So if you're following along in the book, you can follow along then. We also, if you have the book with the disc that goes with it, you'll see that in that disc there are media clips that go along with this chapter as well. And anytime you see this little symbol here, it'll show you that media clip. And for instance, in this book here has at the back end of it, I've got the CD. Hopefully your books have that as well. If you don't have the CD, let me know and I will upload some of these clips to the D2L site. So the book starts off with manual switching, as we do in our class, with the idea that manual means that an operator has to walk up to this switch, which contains this high power. He has to walk right up to a panel, which inside that panel will be the three-phase power that's going to run his motor or his electric heater or whatever he's going to turn on or off. He needs to walk up to that switch and physically change its conditions. And the book starts off with talking about knife switches, old school. This is your Dr. Frankenstein style switch. If you saw any of the old black and white movies, they're always very exciting because usually you can see an electrical arc when they close, especially with very high voltage. And they're usually considered somewhat unsafe these days and quite against code. But that is the essence of a mechanical switch. That is it. The idea that you've got a bar that's on a little swivel on one end that can clamp across and create a connection. In this case, it's showing you two poles or two wires being connected to a motor. That's your classic switch. The reason why we still include that today is on the top of page 238, and I've highlighted this, is the top of page 238 is a picture of what should be familiar to everybody, which is a disconnect box. When you pop open that cover on a disconnect box, you're going to see usually some fuses, 2 or 3 fuses, depending whether it's single phase or 3-phase, and you're going to see a little rotating knife switch. So when you run this lever down to open or close that connection, you're going to see these little knives, little poles swing down and create a connection, just like an old school knife switch. Now, of course, these are much safer because they're inside of an enclosure. The enclosure has different techniques to keep you from doing that while it's open. And so those are little knife switches in there. So that's useful to know. So chapter 212, we get into the manual contactors. We're really just talking about an old school push button or lever style way of open and closing switches. And they go through a description of how they work. That's useful. Honestly, I don't think you're going to run into these very often as manual contactors. They're out there, but they're less and less common nowadays. You will find manual motor starters. We're going to get into that later. But they do mention some key stuff here on page 239, very important. What are the contacts made from? And I will mention that these same contacts technique where you've got your power in and your power out hooked to the bottom, and then on the top, you've got really basically just a plate with 2 little pads on that plate. They lower those pads or raise those pads to make the connection. Right? Hold on, somebody is checking in. All right, I'll get to that later. So silver alloy, low resistance silver alloy is how most of these pads are made. And that oxide, that rust on the silver alloy is actually a good conductor. So those are important fun facts. And they show you a picture here of those pads, that plate with two little pads on them that raise and lower attached to a T-frame to make your physical connections. They also talk to you what the wiring diagram looks like for these big contacts, and they always look like this. Two simple lines on the bottom left of page 240 shows you any as a contactor as just two sets of open contacts. And we see them here as well. Let's jump to 12.3, because this is where we get into stuff that's pertinent to this course more specifically. A manual starter. The difference between a starter and a contactor is motor protection. That should be the number one thing you understand right now. By putting that motor overload protection in the circuit, you convert that switch or that contactor into a starter. A starter allows you to have a higher initial current, the motor is starting up, but then if the motor runs long enough at too high a current, it will blow the circuit protection one way or another. So let's talk about how it's going to do that. It says fuses will not blow. Generally, you want fuses that don't blow when that motor first warms up. You want to size your fuses for that inrushing current. So you need some way of having too much current for too long a period of time, specifically balanced to what a motor really uses in the system. So the older school style, and we're going to take a look at one of those, is what's called a melting alloy overload, where you size the alloy to a certain temperature, and when that temperature heats up, you might get a spring-loaded wheel that allows it to spin. If the alloy is melted, then the wheel spins and pop, that heater coil trips. So it's basically how that works. You can read about it. And then once it cools down, then you can reset it. On the page top of 244, it talks about a reset button that allows you to, once that alloy is cooled down. So these are reusable. They're kind of like circuit breakers, but they're old school. They're also very expensive, and you have to buy them separately from the motor starters. In fact, generally speaking, you buy a generic motor starter for a given very broad range of AC motors, either single phase or three phase. Three phase have three big power conductors. And then you buy one of these little overload devices and you install them after the fact. After you buy that, you have to make sure you pick the right overload device to match your motor exactly. Now, I think I said something last week which isn't quite true. I said you usually set your overload based on the motor current, and that's only true for the modern overloads, like the circuit breaker electronic motor overloads. When you're talking about these old school overloads, you always select based on a variety of factors. In the appendix, they give you a table for that. And that table is on page 728 and 729. So you would pick your motor size based on its horsepower. They'll tell you what probably the typical current is for that motor. And then it will make a suggestion for your overload protection based on factors of either high heat or regular heat situation. If someone is, Cindy, is that you? I'm muting you. There we go. So, so I just want to mention that that motor starter overload for the old school starters, you do a lookup table for that, and it is slightly larger than the motor total current. On page 245, we start getting into some examples of the kind of diagrams you're going to run into for overload protection. A typical way of showing overload are these two little question marks kind of head to head. And it mentions enclosures, mentions different applications. That's useful stuff. But let's go on to page 247. We're going to talk about where the rubber meets the road, which is contactors. Don't forget, a contactor is simply a switch.
Professor, your book camera has cut out again.
Oop, thanks for telling me. Yep, book camera back on. So we're on page 247. We're now talking about magnetic contactors. So contactor is just basically saying it's a big switch, and a magnetic contactor implies that we have a electromagnet. If you use a small amount of current and a smaller voltage, you can control a switch that will control a lot higher voltage and current. And that is why we have a control voltage. We want to have a control voltage through smaller push buttons and smaller switches can turn on and off a big wonkin motor out there. And so that's what a contactor is for. It allows me to turn on and off with a small voltage using a coil and a small electromagnetic. It'll turn on off a big voltage. And this is exactly the same as a relay. A relay is identical to a contactor, except usually relays are configured to handle much lower current, whereas a contactor is designed to handle big current motors, a lot of inrush. And if you're going to buy something to turn on and off a lot of electrical power, a contactor is the way you go. So the book takes you through a typical contactor, and they show you a couple different methods of how a electromagnet, that coil, can control a bigger switch, and they show you three different configurations. Actually, none of these is typical for the kind of big contactors I'm going to tear apart. I'm going to show you what that is. But these are three classic configurations for different kinds of contactors, where that coil then pulls together these two pieces, and that rotates this crank, and that pushes back and forth this bar across those two contacts, and so forth here. So this draws it up and draws it down, and this coil here pulls that armature down against the coil, and then pulls that contact against that movable contact against the stationary contacts. So these are probably all good terms to use, which I hardly ever use, such as stationary contact, movable contact, coil, frame, and armature. They're pretty classically used. Since I generally don't rebuild contactors, I generally throw them out and buy new. Technically, you can rebuild them. The ones I have rebuilt, I basically just replace the contacts or replace the coil. The coils burn out on a regular basis, so they do need to be replaced. But the main purpose for most contactors, you're just going to buy new. I have highlighted on page 248 a simple two-wire control. This is a very important diagram, to understand. Number one, I've broken it into two parts. I've got my high power stuff here, and down below, I've got a line diagram for my control power stuff, right? So let's go through this. at the top of the high power, I've got a control transformer, step down control transformer, nicely labeled, right? You can see I've tied together H3 and H2, and I've hooked up H1 and H4 to the first legs, leg 1 and leg 2 of my primary three-phase power. I'm just using those first two legs to control my control transformer because my control transformer is just giving me my single phase control power, probably 120 volts. They don't specify it here, but it's probably 120. Notice that I've got a little fuse symbol that I always put on my control transformer. That's, that small fuse right there, usually 1, 2, or 5 amps, makes it so that if I short something out down here, then I will blow that fuse before I blow the transformer or melt one of the wires. So that fuse protects all of my control power. Then my legs are hooked to my contactor. You can see these 3 contact points in the diagram. They put a little C next to it, but you don't always see a little C. In fact, the little C is rather uncommon. They give you the labeling of the input and output of the contactor. L1, L2, L3 are pretty typical inputs. Those are hooked to your legs. T1, T2, and T3 are pretty typical labeling for outputs. They go to your motor or whatever your load is. And then they show you these lines going down, in this case, to a heating element set up in a Y configuration. So there are 3 heavy-duty heating coils that all tie together in the middle to give you a 3-phase Y configuration. So this is a really typical 3-phase power transformer for a simple contactor circuit. But they don't tell you how to control it until you look down here. And we can see that I've got some device, they haven't specified what, they just give you a device, open contacts, some sort of switch. When that switch turns on, it sends power into this. This is the coil. I always see a C on it. I usually see it labeled like coil contactor 1. That C means that I'm energizing the coil that pulls down those contacts and make them connect. So when I energize that, these get closed and I get power to my device. So this is a really important diagram to understand what all the pieces and parts are. They show you a little extra piece on here. They show you the wires that would go down that kind of duplicate. They show you that switch here, and they show you where that coil would be kind of here. I don't think it adds any value to show these wires extra up here. This is where you're typically going to see it on most diagrams. You're going to see a separate little line diagram, the fuse for your control power, the switch, the coil, and then the other control power connection X2. On page 249, we have the same thing, more typical for a 3-wire control. 3-wire control means you need slightly more complex control power, and you need an auxiliary contact on your contactor. That auxiliary contact means that I can use a push button and it will latch on the power, right? And then I have an off button that unlatches the power. So this is a very, very important configuration to understand. Number 1, you see your lines in, you see your control transformer, same as last time. You see your T1, T2, and T3 leading to your, in this case, heating element, but it easily could be a motor. And down here, we see our control diagram, the line diagram. We almost always, in a manual situation like this, have a normally closed off push button, which means when it's not being pressed, it's closed. And that's attached to a circuit that has 2 paths. One path goes through an normally open on push button, right? And the other diverts around the on push button to a set of contacts that is built into the contactor. That auxiliary contacts, those extra contacts, when I press that on button, my control power flows through the on button. It's already throwing through the off button because it's normally closed, and into the coil. Then that coil engages the contactors. All these contacts close, and the auxiliary contact closes. So now I got control power that goes around through the auxiliary contact, through the coil, and the coil stays on even after I let go of the on button. That is a typical electromechanical latching circuit. This is probably the single most important circuit in this particular course. Because when you want to turn it off, you just press the off button. That opens up the power, turns off this coil, that opens up this auxiliary contact, opens up all of these 3 primary contacts that lead the 3-phase power into the heating element or the motor, and then it's turned off and stays off. So this is a very typical wiring diagram. I just want to emphasize that. So the book takes you through a couple different types of circuits. A lot of contactors in the US are AC, but more and more we're seeing the DC contactors becoming common, especially in pieces of equipment coming out of Europe. So AC is pretty typical, but more and more you're going to see DC control voltage. So you're going to have a little DC power supply instead of an AC transformer providing you your control power. All right. So the book talks about a couple of issues with contactors. Anytime you have a lot of voltage going across a switch that's opening and closing, you're going to get arc. And so there's different techniques to suppress the arc. Read about that. There's some good stuff in there. Not so much critical for us as technicians or engineers. Very important if you're gonna design these suckers. So you're gonna read a little bit about that. You're gonna read about DC magnetic blowout coils. There are some useful things out there. And you're gonna learn about contactor construction. Talking about silver, cadmium alloys, etc., and copper and so forth. So read about all that. These are 3 typical contactors. It comes in range of sizes depending on what you're doing with them: single phase, 3-phase, or DC. DC contactors have to have slightly different construction. High power DC stuff is its own ball of wax. You always need to make sure that if you're using DC instead of AC, you've selected the right contactor for that. You can't just use the same. You've got to make sure it's rated properly. So kind of bridging over to the next level, on 12.5, we get into the meat and potatoes for the controls industry, which is magnetic motor starters. So the only difference between a contactor and a magnetic motor starter is, of course, the overload protection. This is a classic magnetic motor starter with overload, and the overload in this case is the electronic overload with the dial-o-matic. Obviously it's not called that, I just use that word, current. So you buy these single motor starters. They can handle a range of different motors, and you have to make sure you select the right current to match the current that you are going to be wiring the motor up to. You have to follow the directions for setting the current properly. Generally, though, you would set the current to your motor's maximum continuous current right off the nameplate. But obviously, that would depend on the temperature and the environment and conditions, so follow the directions when setting that current. You have to order this in the right range. If you buy one of these that's set up with a range too large or too small, then you're going to have problems running your motor. Actually, too large is not a major issue, except that you won't be getting any current protection. Your motor will cook before the contactor, motor starter, lets it open up. And so there's a couple different styles of motor protection. This takes you through some of those. You can read about that. They have a variety of trip indicators. Sometimes you get a big red button that pops up. Sometimes you get a little light. Sometimes you get a little like red flash indicator, depending on the method. So each motor starter is going to have a different method of indicating that it's tripped. And some of them aren't going to be very obvious. Talks about setting up the heater sizes, the overload heaters. Heaters is a slang term for that protection. And talks about ambient temperature, like it gets too hot, you need to size them up slightly. And shows you some basic motor starter. This is a large system motor starter. Buy it in its own enclosure. It's all set up with the push buttons on the front, pre-wired for you. You can buy them right off the shelf. In our lab, we have this style of manual motor starter that we've got for demonstration purposes. There's a lot of different other kind of motor protection, like in old school AC motors, especially single phase, you have overheat bimetallic thermal discs attached right to the motor. So if you run that motor too hard and too long, that little bimetallic thermal disc will pop. The motor will need to be cooled, and then you can reset that by pressing it back in again. They are a pain in the ass. They tend to be older motors. And if you get one of these that blows on a regular basis, there's a problem with the coils in there. Chances are you need a new motor. Talks about different ones. All right, so let's get into the troubleshooting. Excellent troubleshooting guide. I can highlight that. Gives you some basic steps for troubleshooting your motor starter. And the final part of chapter 12 talks about what they call modifications. And the most important one for us, for our control circuits, are additional electrical contacts. A lot of times you're going to have in a motor starter, you're going to have a built-in auxiliary contact that you would use to latch in that motor and keep it running, instead of having to have a switch hold it down all the time. That way it's easier and quicker to stop with a stop push button. And you can build safety circuits in better that way. But you might have more complicated, and we're going to get into that in this course, more complicated circuits where you need more than just one auxiliary contact, one extra contact. When the motor starter closes, you might want to have two extra contacts, or even an extra contact that's normally closed, so it's closed when the motor's not running and opens up when the motor runs. And you could use those for a variety of purposes that we actually are going to see in this course for some of the more advanced labs. And here's what a bunch of the electrical contacts look like. And those of you who are in the auxiliary version of this, the totally online remote version of this, you guys are using motor contacts, auxiliary contacts that look like little square bricks, little gray square bricks that snap on to the top of the motor starter. And I'll show those to the rest of you guys, and the rest of you are going to use auxiliary contacts in our motors in the lab, which we will talk about. And the last but not least section here is troubleshooting contactors and motor starters. And we're going to do a section on troubleshooting, and I expect that you guys will have this stuff read through and understand that. I'm not going to read it through you, but it's very much common sense, you know. Inspect, reset, observe, check the voltage, check the starters, check the overload relays. Very much common sense. And there's a little one-page guide for you that you should be able to look up the problem and find the answer to it.